Lesson 2.2, the constant acceleration formulae. Let's look at the objectives of this lesson. The first objective of this lesson is to derive the following four constant acceleration formulae, also known as SUVAT formulae, graphically. So these formulae are known as SUVAT formulae because they contain S, the distance traveled, U, initial velocity, V, final velocity, A, acceleration, T, the time taken. So once we derive these equations, then we go into an example. Then we look at example how to use them to solve a problem with an object with constant acceleration. Let's dive into that derivation of SUVAT formula and their application. The velocity time graph in figure 2.2 below shows part of the motion of a car ride as it picks up speed. Velocity time graph, it's starting from 0 second up to 10 seconds, and the velocity at 0 second is 4 meters per second, and it picks up velocity up to 20 meters per second in 10 seconds. So the graph is a straight line, so the velocity increases at a constant rate and the car has a constant acceleration which is equal to the gradient of the graph. So basically it increases linearly, and this the gradient of this graph is equal to the acceleration. It's a constant acceleration in this case. So the velocity increases from 4 meters per second to 24 meters per second in 10 seconds. So its acceleration can be written as 24 minus 4 divided by 10. That is 24 is the height here, minus 4 is the height up to here. So therefore this height is equal to 24 minus 4 divided by this distance, which is equal to 10 seconds. So that is the gradient of this graph here. So therefore the acceleration is equal to 24 minus 4 divided by 10, which is equal to 2 meters per second squared. In general, when the initial velocity is u meters per second and the velocity after t seconds is v meters per second, as shown in figure 2.3 below, that is initially u velocity, and after t seconds the velocity will increase up to v here. It is constant acceleration again. So therefore the increase in velocity is v minus u, that is velocity at t is v, velocity at 0 is u, v minus u is the increase in velocity divided by the time taken, and the constant acceleration, then the constant acceleration can be written as, which is equal to a meters per second squared, is given by the gradient v minus u, this height v minus u divided by t, which is equal to a. So using this equation we can generate a very important formula, which is equal to, by cross product here, v minus u equal to at. So v minus u equal to at, so which is equal to v equal to u plus at. So which is a very important formula. Velocity after t seconds is equal to initial velocity plus acceleration time the time taken t, v equal to u plus at. So the area under the graph represents the distance traveled. For this journey, the distance traveled by the car is given by the area of the trapezium as shown below. So basically the car accelerates from u to v, and the area under the graph from u to v is equal to this trapezium. So that area can be found by this equation. Basically the height here is 4. At the beginning velocity is 4. After 10 seconds the velocity is 24. So v, this side plus this side multiplied by this side divided by 2 is the area of this trapezium. So 4 plus 24 divided by 2 times 10, which is equal to 140 meters. That is the distance traveled when it accelerates from u to v in 10 seconds. Okay, so in general situation the area represents the displacement s meters. So let's write the general equation. So S equal to U plus V times T divided by 2. That's the area of the trapezium. Again, U plus V times T divided by 2 is the area of this trapezium. So U plus V divided by 2 times T. So we can, there are other useful formula as well. So this is another equation that you can use if you want to find the distance. If you know initial velocity, final velocity and the time taken, you can find the distance. And then we can actually generate few more equations. For example, you might want to find the displacement S without involving V. So sometimes you may not know the final velocity in your calculations. This can be done by looking at the area under the velocity time graph in a different way, using the rectangle R and the triangle T as shown in this figure 2.5. Please look at this figure. So we earlier shown that U is the initial velocity and V is the final velocity, and we took the area of the trapezium by taking U plus V times T by 2. Now we take it separately, like T is the triangle here, R is the rectangle here. So the area of this triangle can be found by actually, because this distance or this height A to C is V, the final velocity, but C to B is U. Therefore, if you take away U from V, we get the distance from A to B, V minus U. So V minus U is actually the height, that is AC equal to V, the height from here, this point, and BC equal to U, that is we know that, and then AB is equal to V minus U, and then from equation 1 what we know was that V minus U equal to AT. We actually shown it here, V minus U equal to AT. So we can replace V minus U with AT here. So that's what we did here. So therefore we can calculate the area of this triangle without involving V, because we have V minus U equal to AT. So then we can find the area T is equal to half. So the area, so basically the total distance travel is total area is equal to total area, which is equal to area of R plus area of T. Area of R is the rectangle here, so we know that rectangle height is U and the width is T, so it's straightforward. U times T is the area of rectangle, and area of the triangle is half times the base times the height. So base is T, half T times AT. So it's interesting here. So what we see here is that you generated the other very useful formula, S equal to UT plus half AT squared. So UT is the area of the rectangle, this one here, rectangle R, and the rectangle T has triangle T has area of half T times AT. So half T times AT equal to half AT squared, and then UT, which is a very important formula, S equal to UT plus half AT squared. In some cases, please note that we put S equal to S0 plus UT plus half AT squared. So S0 is the initial displacement. Then most cases our initial displacement is 0. Therefore, we can easily use S equal to UT plus half AT squared. So now to find a formula which does not involve T. So all these equations 1, 2, 3 had T as part of the equation. So in here we saw that S equal to U plus V by 2 times T, and earlier we saw velocity V is equal to U plus AT. So if you have a question which you don't know the time, so you can actually use an equation without T by eliminating T. So what we are going to do now is to find a formula which does not involve T. You need to eliminate T. One way to do this is first to rewrite equation 1 as here, V minus equal to AT, and V plus U, equation 1 and equation 2. Equation 2 we saw this equation, very similar equation, which is equal to U plus V. Actually we can take into one side, so and write this one like this here, U plus V. So when you cross multiply 2 go there, 2s divided by T. So then what we can do is then and then multiply them gives, we actually when you multiply one by the other, this is like A minus B times A plus B equation, that is A squared minus B squared. So here When you multiply v minus u, v plus u, right side, left side, and right side is at times 2s over t. Interesting, isn't it? So you can easily eliminate t from this equation. So when you multiply at with 2s over t, so t will cancel off. This will become 2as, and the left hand side is equal to a squared minus b. A minus b times a plus b is equal to a squared minus b squared. Basically middle terms will cancel off. You have v squared minus u squared equal to as, so we get this final equation, v squared equal to u squared plus 2as. That's equation number 4. Very important formula, which does not involve t. So when you want to solve questions with which you don't know t, you can use this equation. That means here you have to know, you can calculate the final velocity if you knew the initial velocity and the acceleration and the time traveled, so distance traveled. You might have seen these equations before. They are sometimes called the SUVAT equations or equations of formulae, and they can be used whenever an object can be assumed to be moving with constant acceleration. Please note that these are for constant acceleration. Let's take an example. Question 2.2.1. A bus leaving a bus stop accelerates at 0.8 meters per second squared for 5 seconds and then travels at a constant speed for 2 minutes before slowing down uniformly at 0.4 meters per second squared to come to rest at the next bus stop. Calculate the constant speed, the distance traveled while the bus is accelerating, the total distance traveled, all these things. I think best thing is to plot them in a graphical form, because the bus is leaving at a bus stop which accelerates at 0.8 meters per second for 5 seconds and then travels at a constant speed for 2 minutes and before it's slowing down uniformly. So you can actually visualize it goes up that way and stay like that and go down. So please look at how to draw, and this is how you will finally get is actually this is the linear way of representing it. It has a initial point which has a 0 velocity, 0 meters per second, and then after that it accelerates in a acceleration of 0.8 meters per second squared for 5 seconds, and then it reaches the next destination B, and then we don't know the exact velocity at that time. So the diagram shows the thing in linear way. You can actually plot them time versus distance, but here this is how we can represent it straight away. But here let's the constant speed be v, because we don't know after that it travels in a constant speed, so before it decelerates. So what we want is to find the v. So what we know is the u, that is we know that it started at the 0 velocity and it traveled 5 seconds and then it had an acceleration of 0.8 meters per second squared. So what we know is the initial velocity, time, and the acceleration, but we don't know the final velocity. So what we need to know is, like, we don't know the distance. So distance is not given, s is not given, so because it only gives that the time it took to reach the next destination, 5 seconds, and the acceleration and the initial velocity was 0. So therefore we definitely cannot use the first equation, which is v squared equal to u squared plus 2as. So we use v equal to u plus at. In this case we know u, we know a, we know t, so therefore we can find the value of v. So substituting these values in this equation, u is equal to 0, a equal to 0.8, equal to 0.4, t equal to 5, so we get the value of velocity after it travels t seconds, 5 seconds. When it reaches point B, it is equal to 4 meters per second. That is, the constant speed is 4 meters per second. So please look at the question again. So it travels 0.8 meters per second squared acceleration to 5 seconds and then travels at a constant speed of 2 minutes. Constant speed of 2 minutes. So then it's when it reaches the velocity v, which is the 4 meters per second that we found just now, and then it will have a constant speed for 2 minutes before it starts decelerating. So now let's take the next part of the journey of the bus. Let the distance travel be s1 meters, because we try to use suffix 1 because there are three distances to be found. That is the time that it accelerates and go in the constant speed and then decelerates. So s1 is the time that it accelerates. So if you want to calculate the value of s, we know that u equal to 0, t is equal to 5 seconds given, acceleration a is given 0.8. Therefore we can use, because we cannot use s equal to half u plus vt. In this case, we found the value of v in the previous question, but we can actually easy if you use this one, because in case you had an mistake in the first part, you may be in trouble calculating the s value here. So therefore best to use the second equation, s equal to ut plus half at square. So you get the value of the value s1, that is the time of distance during the acceleration. U equal 0, t is equal to 5, and then this value 0, half at squared, 0.2, 8 times 5 squared, 10. That is the value of s1. You could have actually used this one also to see whether your answer was correct earlier. Half u was 0, our value of v was 4, and then 4 divided by 2 is 2, and then times the t is 5, 2 times 10 is 10. So actually we can verify the answer that you got earlier, which was 4 meters per second after 5 seconds of travel. It's also can be found in this equation. The value of s was the same. So the bus accelerates over 10 meters.
Now let's look at part 3. The diagram gives all the information for the rest of the journey. Starting from B, we came from A to B with acceleration. From B to C, it is constant velocity. It is found that the velocity at B was 4 meters per second. Therefore, up to C, it travels at the same velocity, 4 meters per second, for 120 seconds.
Up to D at a deceleration of 0 meters per second squared. So this is what is given. So we don't know the second time taken for deceleration, and there will be a s2 time. That is it actually travels. Sorry, in fact this one is s1. So earlier I said s1. This is the s1 value of 10 meters s1. That is the time taken to reach from A to B. We need to find the time taken to reach from B to C and C to D. Between B and C, the velocity is constant, so the distance traveled is also given by the multiplication of velocity times the time taken. So velocity 4 meters per second times 120 seconds, so it traveled 480 meters during the constant speed time, B to C. And then from C to D it decelerates. That is the distance between C to D be s3 meters, and we want to find s again. So how much distance it travels during the deceleration, C to D. So we know that u equal to 4 because we found the u, the constant velocity. It actually starts at B to C are same because it's constant velocity 4 meters per second. And then A is the deceleration minus 0.4 meters per second squared, and then the initial velocity is 0. That means the bus comes to a stop. So that means at this point it becomes 0 meters per second. So that's information given. We want to find the distance, so there are a few equations you can consider. V equal to u plus at. You cannot use it because we don't know the time taken because t is not given, and here also t is not given. You can't use s equal to ut plus half at squared. We can't use this equation, you still don't know t. Therefore we can use v squared equal to u squared plus 2as. So using that equation we can find the distance traveled. So u equal to 4, a equal to minus 0.4 deceleration, v equal to 0. So to use v squared equal to u squared plus 2a. So we substitute the values and we can find the value of s3, which is equal to 20. So after simplification we got 20. That is the distance from C to D is 20 meters. So we found S1 was 10 earlier, S2 B to C is actually 480 meters, and S3 now it decelerates for 20 meters. Distance taken slow down is 20 meters. Therefore, the total distance traveled is equal to 10 s1 plus 480 s2 plus 20 s3, 510 meters. So these are the questions asked. I think this is the final part of the question. It asks us to find the total distance traveled. So constant speed, the calculate the constant speed, that is it accelerates and then take constant speed for 120 seconds. So that speed we found v is equal to 4 meters per second. The distance travel while the bus is accelerating, we found it to be equal to 10 meters. This travel is 10 meters, and then total distance is basically we have three parts. First distance is s1, and the second one is s2. First one is s1 is 10 during the time of accelerating it spent 10 meters, and then during the time it moves in constant speed. We calculated the distance traveled is 480, and then during the time it decelerates we found s3 is the time the distance, which is equal to 20. So total distance is 510 meters. Okay, so you can actually have more information from this reference book, Cambridge International A's and A-Level Mathematics by Sophie Goldie, and the series editor Roger Procus, published by Hodder Education. Thank you.